Okay, so one major concept that we really want to have down. So this is like a definition, okay, that we need to know. It's going to be showing up for the rest of calculus, and it's the idea of continuity or being continuous. Okay, so I'm just going to write the word continuous here. Okay, so for the definition. And we're going to talk about this as continuity at a point, or being continuous at a point. You can talk about also intervals, like being continuous on an interval, but right now we're just going to focus on continuity at a point, because intervals is just basically a generalization of point. So, continuous. A function is continuous at x equals c if there is no interruption, I think that's 2 R's, interruption in the graph of f at c. That is not an official math definition. That's more of like a, plain English with a little bit of math thrown in, I guess. Okay, so a function is continuous at x equals c if there is no interruption in the graph of f at c. So what do I mean by interruption?
Discontinuity.
So, for example, no holes.
If you have to pick up your pencil.
Right, exactly. No jumps. No. It's the exact idea of having to pick your pencil up. No asymptotes. That's right. Asymptotes has a P in it, oddly enough. I don't know why. Or gaps, right? I guess you can also say gaps, too, is like kind of like a discontinuity. Okay. Holes, jumps, asymptotes. That's what we're going to mostly focus on then. So then in the definition, the actual definition though that we want to kind of focus on, these 3 properties. Okay? So a function is continuous at C if, okay, so continuous at a point C. So there's like the more official kind of mathematical definition. We need to have these 3 properties ingrained in our brains. So we just need to know these 3 things that must be true. Okay? So for a function to be continuous at a point C, 1, f of C is defined. You can also think of that as it must exist. So f of c has a value. So when you plug c in, f should work. It should give you a number, a value. Okay, so f of c, at the value c, you should have a value. When you plug in c, you should have a value. Okay, so at c you have a value. As you approach c, so the limit as x approaches c of the function must exist. Okay, or again, you can say defined or whatever. Okay, the limit as x approaches c of f of x exists. So again, at c, the function must have a value. As you approach c, the function must have a value. Okay, and then third, so the function value must exist, the limit must exist at c, and then finally, the limit value must be the same as the function value. So yes, the function can exist. Yes, the limit can exist, but this third one can still fail. They don't necessarily have to be the same thing. Okay? So the function may go to a certain value at c. The function may go to a certain value as you approach c, but they need to go to the same thing if you then have to have all 3 of these properties together. Okay? And that then would show that the function is continuous at that point c. Okay? And then for the interval, a function is continuous on the interval AB. I'll do the open interval. If f is continuous at each point in the interval. Right? So there we've kind of generalized we've kind of generalized our original definition. This original definition is just for continuity at a point C, one point C. We can talk about continuity over an interval, though, basically if f is continuous at every single point in that interval. Okay, so we call that then, if f is not continuous at C, then f has a discontinuity at C. Right? And there's two main discontinuities that we are going to look at. Okay, so the two main discontinuities we're going to consider are the removable discontinuities okay, and then also the non-removable discontinuities.
Someone was very creative coming up with these names.
Right, well in math we don't like to mince words, right? We just like, it is what it is. Okay. Bless you.
God bless you.
So let's consider a function here, and let's see. We'll use a piecewise function. A piecewise function that's so simple it's complicated. We'll sketch this here too. Okay, so let's sketch this. Not very straight. So let's see, for my x-coordinates, I better at least have a 2. I better at least go out to 2 on my x-axis, right? Because at x equals 2 is where we have this kind of change. Okay. And then on my y-axis, what's the highest I need to go? Yes, the function value, right? F of x is equal to 5 here, so oh boy, I didn't leave myself enough space, I don't think. Yeah, I'll just make it a smaller kind of scale. Okay. Okay. And again, there's 1, 2, 3, 4, 5. Okay. So, the function f is equal to 3 for every x value that's not 2. So that means, for example, at 0, what's my function value? 3. And at 1, what's my function value? 3, and we'll skip 2. What's 3 at my function value? 3, and 4 is 3, okay? So we can kind of see that going this way, and going this way. All right, now 2, well, certainly I can get a little bit closer than just that 2, right? I mean, it doesn't stop at 1 and stop at 3. So, for example, you know, at like 2.1, well, 2.1 is still not 2, so it's going to be 3. So really, I'm going to go all the way up to 2. I'm just not going to get there. And so what should I represent then?
A hole.
A hole there. That's right. Right above the 2, there should be a hole for the x equals 3, or for the y equals 3 kind of line right there. It's a horizontal line, y equals 3. And then that's that top part graphed, right? So wherever x is not 2, so open circle there, and everything else is just 3. At 2, we have 5. So at 2, up here to 5, and we'll just put a dot. Okay? So this is a removable discontinuity right here. We can see where is our function discontinuous. At what x value? At the x value 2, right, our function is discontinuous. So this thing, put this in the wrong color, there you go. That is our discontinuity, right there. Okay, and in fact, in general, the removable discontinuities we'll be dealing with are holes in our graph. Okay, so what is that? Why do we call that removable? Well, because the idea is, with a hole, you can fill in a hole, right? You can like say, to make this continuous, what point do I need? I need the point 2, 3, right? At 2, it needs to be about y value 3, and that fills in the hole and makes it then continuous. So we can remove it by kind of filling in that hole. Okay. Now, granted, it wouldn't be a function anymore. We have to adjust our function. But the idea is that we can kind of fill in that hole. Okay. Let's compare or contrast that with a non-removable discontinuity. So let's see an example of that. So let's talk about the function 1 over x. Okay, so 1 over x, that's one of our family of functions that we should know the graph, right? Right. We should be able to transform it to, maybe I'll shift it left, up, right, down. Okay, I don't know why I went in that order, that was weird, but oh well. Okay. So 1 over x looks something like this, right? Okay. So is this function continuous everywhere? Yeah, right. It's kind of like, that's kind of a silly question because we just put it in the non-removable we put it in a discontinuity section. So if I had done that and it was like, actually it's continuous everywhere, I'm like, why we write it there then? So, all right. So where is our discontinuity? At what x value? 0. And is that the only place where where this function is discontinuous?
No. It's like an infinite number of places.
Why?
Where else? What other x value is this function discontinuous? Right, it's just 0, it's just 0, it's just 0. Yep, it's just 0 here is where it's discontinuous, okay? So x equals 0, okay, is a non-removable and you can see here the difference in kind of like the nature, okay? You can just see like the picture, right? Okay, there's no easy way to fix this. There's this asymptote. It goes down to, our function goes to negative infinity from the left and positive infinity from the right, and there's no way to really fix this. There's no way to kind of fill this in, okay? And so thus the kind of the nature of this non-removable discontinuity. These tend to show up as like asymptotes, okay, or jumps. They also can show up as like jumps and like a piecewise function. If you have like one function and it jumps up, like the graph of the well, what was I going to say there? I can't think of anything. Like some of the piecewise functions we talked about before, but there are jumps and stuff like that. It's like a piecewise function, kind of, you know, if I do a quick sketch, if it goes like here and then there's this dot and then it jumps up. Right, this is a non-removable discontinuity. Sorry, I'm going to scoot that over. This is non-removable discontinuity because you're jumping from here all the way up to here and then continuing on. Can't really fix that. Okay, there's no hole to fill in. I mean, there's a hole, but to be filled in, it's not a function anymore, and it doesn't make them join up. You still have to jump. Here, to fix this discontinuity, all you got to do is just fill in that hole. Okay. Other ways, and so actually, let me backtrack a little bit here. Other ways removable discontinuities show up. For example, okay. If you have a function like g of x, I'm just going to squeeze this in over here. G of x equals like x squared minus 1 over x minus 1. Like this. Okay. Looking at this function, what x value is going to give us a problem here? 1, right? It's restricted in the domain, right? It's a domain restriction of 1, x can equal 1. But if x could equal 1, right? If we do include 1, that means we have a discontinuity at 1, right? Because at 1 we're undefined. So that when you're undefined, that indicates you have a discontinuity at that point, okay? But the nature of this, though, what can we do to this function? We can factor, right? We can factor this out. Okay. And so like this, if I cancel those x minus 1s, I'm left with x plus 1. Okay, now granted I did a little bit of fuzzy math here, right, by saying that x plus 1 is the exact same thing as x squared minus 1, right, over x minus 1. These two things are not equal as we really should understand equal to be. Equal should be the exact same thing. This thing, this original function, has a discontinuity or a domain restriction at x equals 1. This thing, does it have a discontinuity at x equals 1? No. Does it have a domain restriction at x equals 1? No. So they're technically not exactly equal, but we can say they're equal because they're equal at everything but x equals 1. But the point of this was to show that this thing has a removable discontinuity, and here's kind of like the whole removable idea to it. You can get rid of the problem and then have this function. Okay, and so this function kind of fixes what the problem was in there. Okay, it kind of helps you fill in that hole. So this lets you know what y value will kind of fill in the hole. Okay, so if you plug in 1, 1 plus 1 is 2, so the point 1, 2, okay, will fill in, okay, the hole.
Does it have to be 1? Could it be like you plug in 2 and it's 2, 3?
Well, 2, there's no problem, though. 2 is not where the hole is located, right? Because 2 works here, but 1 is where the hole is located in this one, so 1 is the hole, but the 2 is the y coordinate of the hole.
So you have to plug in what doesn't work.
If you want to fill in the hole, if you want to make it continuous, okay, then that's how you figure that out. Yeah, Brandon.
So what happens if it's like x squared minus 3 and then...
Over x minus 1?
Yeah.
So great question. Let's take a look at that. So I'm going to show that in my graphing calculator here real quick. So let's just see. So if I have x squared minus 1 over x minus 1, and let's change it instead to be, well, so I'll have that graph, and I'll do x squared minus 3, you said, divided by x minus 1?
Yeah, just so I wouldn't factor.
So right, so do you see what Brandon's doing here? So this doesn't factor, and it won't cancel with the x minus 1, so let's see what happens. And in fact, if you guys didn't know this, when you want to graph two different things and compare them, you can arrow all the way over and change the way it's graphed. I'm going to hit enter once, and it thickens this line. So this line will be thicker, so it'll be easier to see. I'm going to zoom 6 there to fix it. Okay, so there's our first one. And there's the second one. So you can see the first one, and it's hard to see, but there will be a hole there at 1, 2. So at the x value of 1, there's a hole. But notice now, in the second one, there's now an asymptote that shows up. And so that means that when you write it, this one has a non-removable discontinuity because you can't cancel it out. So it becomes an asymptote now. Exactly right, because we can't cancel it out. It's not removable, so it's non-removable, becomes an asymptote.
What if it's like not a hole? What if it's like an entire gap?
So like a space between the pieces. So okay, so Caleb's question real quick here was like, what if we have like a piecewise function maybe, and it's like a dot right there, and then over here it picks back up and like goes like that, and there's like a space between those two. So this would also be non-removable because there's no easy kind of way to fix it. There's no, basically a removable discontinuity is essentially, for our purposes, it's just going to be like a hole, and then the gap would go in as a non-removable discontinuity. Yeah, really just the removable is just the hole. Just the hole. Okay? So I wanted to summarize something here real quick. So basic idea here is that f can be made continuous. Okay, f can be made continuous by approximately, so f can be made continuous in this case by defining or redefining, whoops, and I wrote the word by twice, by defining or redefining f of c. Okay, so f can be, oh, sorry, you can't see that there. There it is. F can be made continuous by defining or redefining f of c, and in these cases, for non-removable, f cannot be made continuous. I'll put that like made in quotes there. Okay, f cannot be made continuous by defining f of c. Okay, there's no way to fix this hole, or this gap, this jump, this asymptote. There's no way to fix that. Here we can fix that by just defining, oh, by the way, at 2, you have a value of 3. Fix that point. Okay, no way to fix it. Okay. Right. So, yes, I think, is that as far as I wanted to go? Let me see. I'm getting a little mixed up.
I think we're good.
Yeah, I think we're good? Okay. Well, so actually, I have a little exploration here that I forgot to copy, so let me go make copies of that real quick, and I will be right back, and you guys can, like, then work on this, okay? So I'll be right back. 1 second.
Alright, you're good, man. Let's talk about we're gonna have fun. 11 messages in 3 conversations. What? Look at all these condones.
You're both sucking.
Works for me just fine. Oh, it's still on airplane. Let's roast it up.
Only we could name some jobs. Ryan roast that shit.
How many? I literally, like, the whole time I'm, like, trying to pay attention here, I just heard you guys, like, whispering back here and giggling, and I was
Where did he
like,
go?
Oh, he's making back. All I hear is, Ryan.
What?
Which is why.
Your arm was longer that one day, I smacked my thumb leg.
It's just like Ryan.
What?
I meant to tell you that, but I haven't been, I keep forgetting.
What Arnold Palmer?
You're like that big Arnold jug a couple weeks back, stabbed my gum.
I drank that all day.
Wow, it's just been clean. I feel like I'm straight and all that. I meant
Put
to
that in
tell
the
you,
jar.
I keep forgetting.
Okay.
Is it really?
No, it is just like a waste of ink.
So take one of these.
Oh, quick.
Now let's take a look at, yep,
Copies quick.
Yeah, boy.
Even better.
So I wanted to go ahead, and we're going to work to this. This is kind of like you guys work on together. Okay, I'm not going to like do this too direct. I'm not going to write you Oakdale. Ooh.
You better lose.
I'll be there after work. Are you going?
What? I'm on the team.
Oh!
So
Dude,
he
I
will
literally
be
ask you that
there.
every day.
He'll be there.
There you go.
You going to the game?
I'm on the boys' team.
Play at home.
I was thinking it was.
You're gonna be there.
No, we're going to the girls' game, I thought. Because remember,
The trainer is going to the girls' game.
I know, I don't work with him today.
Oh. Oh, you're talking about
I have to
going.
go to work, yeah, because remember, like,
Yeah.
the whole, what? Yeah, I'm going to FSK on Friday.
We gotta get our graphic calculators out for this one.
Yeah. You may use your graphing calculator. It does say to let you like to adjust your window and stuff like that. So would not be a bad idea to have that
Alright.
handy.
X squared minus 1. Graphic calculator. Can you use interval notation in a piecewise function?
No, you normally use inequalities when you do.
Or can we do it towards negative infinity and infinity? Or no? Because, what am I thinking?
Zoom 6 like takes you to the normal viewing window. But if you want to zoom in on a certain area, zoom box is what you want to use, yeah.
That's right. Not equals 1.
Yes, sir.
Can I borrow a calculator? My sister took mine.
Mm-hmm.
And now she actually is here.
Oh, okay.
How should f of x be defined?
Is 2 just a direction, or do we have to like write something down?
Sorry, let me see. So just, yeah, kind of like prove to yourself that there is a discontinuity there. Convince yourself using the table or the graph at least that it does, yeah. But there's nothing to write yet.
Oh, that's why I didn't make that.
So we've kind of gone through this example already in my little, discussion there, but...
I was looking at the graph, I was like, what? Am I getting
Okay, to get stuck on something, I'll come around to help. Ooh, let me put in flex.
Oh, Ethan's gonna be pissed.
Oh, snap. That's nothing that you have.
Yeah, I know.
You went too many times.
Wait, is this correct?
Let me see, I've got that paper here. Let me see what you got again. And we're going to go over it together here, so.
Why'd you say you were?
I'm sorry.
Sandwich?
Yeah.
Looks good. Mm-hmm.
Yeah.
Tyler and Christian.
What is it? Do my lunch college and the lunch.
What is so bad?
I was, and I asked who I have lunch with. Yeah, what kind of bite is that? How are you gonna take a bite and eat that out of a sandwich? That's weird. What person does that? How are you gonna eat a sandwich like that? Yeah. I have enough for now. I'm good for like a day. have like kind of just stare at the camera. Oh, I can't.
This? It's called. I don't think it's on my phone.
I have Chris calculator.
It's called Wabbit.
Anybody want to be, does anyone want to be put in for flex today? Any requests? Okay. Negatory.
Oh, I want to come.
All right. Very good. Thank you, Emma. I got you. Nate, I put you in, bud.
Is there homework? Yeah, there's gonna be homework today, right? Yeah, I'll come. So I'll do my homework.
Okay.
Are you going to Mr. Davies?
No, it wasn't.
Do I have cheese? Oh, probably.
Okay, guys, like 1 or 2 more minutes here, and then we'll go over this and try and finish up. Okay.
Is there a back?
There's no back. It is
You could just look at the text.
empty. Donovan, question? I'll be right. Oh, I'll put you in. Thank you.
Would you go for the first one? Yes. No.
Got you, Matt.
When you plug in 3, you don't get 4. Okay.
Maybe she went a week or only if it counts.
Yeah, sadly. Yeah. I like having 2. It's nice.
What?
I like
Yeah.
having two too.
I love calculus.
Then she can talk.
Yeah.
The other class. You can put just like that.
Yeah, sadly, I had 40 AV students last year, and now I have 15 AV students this year. Apparently, I'm a terrible teacher, and people want to avoid me. Because of the Common Core stuff. That's what I thought, too. There's like a Common Core bubble that you guys are kind of like working through right now.
I wonder what the average grade of fast calc is.
Probably a lot lower than the average.
I know a lot of people are failing.
Yeah.
Yeah, even like Riley.
It's tough when you start out. It's because the fast pace and
Quinn's like shooting for a low A.
A plus.
It doesn't
I would
even.
shoot for a low B.
I would be shooting for like a. Yeah, I would be shooting for like a.
Okay.
Doesn't Ethan have like?
let's take a look here real quick.
Yeah.
What?
It's probably the lowest grade Ethan's ever had.
Okay, so the domain of F, right? Interval notation is fine there to describe that, right? So it is negative infinity to 1, a union 1 to infinity, as is not continuous at x equals 1. Okay, so it is not continuous everywhere, it's not continuous at x equals 1. Okay, step 2, that's on your own, just to convince yourself. Again, we kind of talked about this one already, so we saw it already somewhat here. How should f of x be defined at x equals 1 to remove this discontinuity? So f of 1, what do we want it to equal? We want it to equal, well, 2, right? We want it to equal 2. Okay? There's a couple ways you can do it. You can use your table and use the, approach the x value of 1 to do like 0.9999 and then 1.00001 and see what the function value approaches. And the limit's approaching 2, so we want our function value to also be 2 to make it continuous, right? Because again, the limit value and the function value both must equal one another. Okay, so if it looked at the limits approaching 2, we want our function to be 2 at 1. All right, then we factor and then compute the limit as x approaches 1, and so it gives us 2, which is what we could see there. And so there's how we can define it in a piecewise function to make it now continuous everywhere. We say it's our original function for every x value where it's not 1, basically, because 1's our only problem. And then you have kind of 2 options here. You can either choose to just say 2 at x equals 1, but you could also say x plus 1 at x equals 1, because that's like the, the factored version there, right? You can use the x plus 1. And why is that true? Because remember, this function and the x plus 1 are equal at exactly every single point except at 1. So x plus 1 is how you fix it, so you can use the x plus 1 there instead. Cancel that first. Okay, and so then there are the 2 others here, okay? So A is not continuous everywhere. If you look, okay, at 3, yes, the x minus 3's cancel. Yes, x minus 3's cancel, but when you plug in 3, you get 3 plus 4 is 7, and that is not what we get here. We get a 4. So this is not continuous everywhere, okay? Because the function, okay, approaches 7 as you approach x equals 3. The limit here is 7, but here it's supposed to be 4, so they don't match up. The function value at 3 is 4. The limit as we approach 3 is 7, so they disagree. Function value is 4 at 3. Limit approaches 7 at 3. And then letter B, okay, this is continuous everywhere. Okay, the function value of -2 is 0.5, and as you approach -2, we have to do like the multiply the conjugate there and take the limit essentially, and you approach 1/2, and so that does match up then. So they do match up. This little piece does fill in that hole right there. Okay, questions on any of that? Yes, I'm sorry about that. And then move my hand out of the way, that would also be helpful. Okay, if there are no questions, then let me give you guys your assignment here. Let me see if I can figure out which one is which. Okay, yep, I think I've got it here. Okay. So let me give you an assignment from the book, and then also I'm going to give you a piecewise function that I want you to evaluate. So I'll stop the video here. Remember, like and subscribe.